And it is my pleasure to introduce Martin Möller, who will speak about spectral decomposition for strata, the case of Mark tori.
Thanks, Claire. Thanks for the invitation to speak here. Apologies to those people, maybe mainly from Darmstadt, that have already heard a version of it. So I'll report on joint work with Jaydev Atreya, Jean Lagacé, Martin Raum, on something that is very classical for the modular surface case, which I will recall then first, which is spectral decomposition, decomposition of the L2 space. And the goal is to do that in a non-classical context, at least for the number theory perspective, namely the case of strata of differentials, and highlight what Siegel-Veech transforms are in that context and why they are something that is very familiar with those who have a number theory background. In the end, we can do only a baby case, the case that I call H00. If I write H00, maybe you would should keep in mind Jacobi forms, the Jacobi plane. I'll give the precise definition. So that case is, in some sense, does not present any of the true challenges that we will encounter when doing it for strata of differentials, but it provides us with a lot of warnings, what we should do or expect or not expect. So let's get started. Let's look at the modular surface, which is the double quotient of G SL2R on one side by its maximal compact group K, and on the other side by SL2Z. And if nu is the Haar measure on G, it descends to a measure on X. And with respect to that measure that I will also denote by U, we can describe either the L2, we can ask to describe the L2 space either of X or of G mod gamma, which is doesn't differ much from X, which it's the unit tangent bundle to the modular surface. And I will pass back and forth between the two, both for the modular surface and later for strata, because yeah, depending on the context, things are described easier on one side and on the other side. You can lift functions from one side to the other, and functions that are invariant under the group K descend properly to functions on the modular surface. And if you're not invariant under K, but have a certain K type, means act by a character of K, then you don't actually descend to L2. But I could, oops, that was the wrong button. That was, then I should introduce some spaces of L2 functions with modular transformation behavior with respect to a K type K, and then really get in the correspondence. I will sweep this under the rug often, but if you have questions about that, please ask about this and anything else. So what does it mean to describe? To describe, there's two ways to do it. Either those people that say, like representation theory, they might want to classify the representations that occur together with multiplicities, and we all know the SL2 are representations, except that besides the trivial series, discrete series, and principal series, I forgot the bad guys, the complementary series is also there. So the classification of SL2R representations is very well known, and there's the question of which of those representations appear in these L2 spaces. On the other hand, you can also say I have the Laplacian for the hyperbolic metric on H acting on L2 spaces, and you can ask which subspaces provide continuous spectrum, provide the discrete spectrum, and then you can ask tons of refined questions, like what is the smallest eigenvalue, how many eigenvalues of the discrete spectrum do you have below a certain range, the eigenvalue growth, and then construct eigenfunctions and so forth. These are much more refined questions than I will be answering for strata, so let me not mention more of the detailed questions, but just state the rough answers, which appear, well, in any classical textbook on L2 decompositions. So there's the space of cusp forms. These are the L2 functions that for the horocycle around the cusp, which is nothing but integrating the x variable from 0 to 1, give 0. So this is the space of cusp forms, and the other player, the complementary player, is the space of Eisenstein series. And actually, I want here truncated Eisenstein series. So for a function psi with compact support in 0 infinity that will serve as a truncation function, I consider the usual summation for gamma in the cosets of gamma by gamma infinity, the stabilizer of the cusp at infinity. And instead of summing just the imaginary part of gamma tau, I will truncate that by a function psi. Again, here this is the invariant version by adding the corresponding weight k modular factor. I get also the Eisenstein series in weight k. Let me gloss over that and define the whole space, the Eisenstein space, which is the closure, the L2 closure of all these truncated Eisenstein series for all functions psi. And then I summarize what you have in all textbooks on L2 of the modular surface, namely that there is an orthogonal decomposition of the whole L2 space into cusp forms and the Eisenstein series. Let the Eisenstein series itself decompose into the constants, and the image. Should be the image, not to be confused with an imaginary part of a copy of L2 space of R plus with its Haar measure. And let me also remind that this is a non-trivial theorem, because this requires analytic continuation of the Eisenstein series until we hit the imaginary axis, and then you can provide this isomorphism using the Eisenstein transform, integrating along the the axis with real part equal to 1/2. And this is and then on the spectral side, we know that the Eisenstein series provide the continuous part together with a isolated eigenvalue 0. Continuous part, in fact, starting at a quarter, whereas the cusp forms provide pure point spectrum eigenvalues going to infinity with finite multiplicities. All this is very classical. I didn't check to when it goes back to, probably almost a century. And I would be very happy if I could have an analog of that statement in the case of strata. Just that, no more refinements would be great. So, as I said, there is more refined questions that you can ask for the modular surface, explicit constructions of cusp forms, Weil's law for the growth of eigenvalues. There's other generalizations that are orthogonal to what I want. You can change the group SL2Z for other cofinite Fuchsian groups. where several cusps enter the picture, and then the fact that the residual spectrum and the scattering matrix enters the picture. You can go to covers and see what that does. For example, the congruence covers and what that does to the spectrum and the lowest eigenvalue. Or you can change the group to higher rank groups or even p-adic Lie groups, and starting with a work of Langlands and an uncountable of number of people that I just abbreviate with the dots. At least in the case where G is a semi-simple Lie group, there's a lot known, and all this is totally orthogonal to what I really want to do here. Okay, so let me start by stating what I really want to do here. I consider a different space. I start with a moduli space of curves MG, and I consider over it the total space of the Hodge bundle. The total space of the Hodge bundle is a space of points consisting of a Riemann surface. X is just a Riemann surface of genus G. This G together with a section of the canonical bundle, together with a holomorphic one form that I usually call omega. And the good thing about that space is that points in that space can be visualized very easily, very, very visual. I can just picture you an element in that case. Let me take the case of genus 2. So I take a genus 2 surface and I just draw you such a thing. Such a thing looks, for example, like the following polygon. Well, the polygon, this is certainly a polygon that I've been drawing here now. A polygon is certainly not a genus 2 surface, but if I identify sides by parallel translation, for example, I glue this side to this side, I glue this side to this side, number 3 to number 3, number 4 to number 4, number 5 to number 5, then I already have a closed surface. And you might be wondering what happens at the corners. Well, just topologically, this point will be identified with this point because of the number 5 identification, will be identified with this point and this point because of the number 2 identification, and also with this point and this point because of the number 4 identification. That point, I shouldn't have done the last thing. And in the same way, there's a second point, namely this point, that gets identified where I'm drawing a thick black dot. So there's two special cases. That's why I wrote mu equals 1, 1, which means that the holomorphic one form dz, if you consider this inside the complex plane, gives a one form on the surface obtained by gluing it, and it has two special points. In fact, 2 zeros, as any differential form on genus 2 has, at least counted with multiplicity. So what actually happens here is that the space of omega mg, the total space of the Hodge bundle, minus the 0 section where the differential omega is plane 0, decomposes into strata according to the number and multiplicities of the zeros. So in genus 2, there's two possibilities. We can either have a double 0, or we can have two simple zeros. These are the only two partitions of the number 2. And in general, there is all those partitions of 2g minus 2 into a tuple mu called m1 through mn. And these are the strata of differentials. They are nice spaces, nice manifolds. We'll compute the dimension along with the next thing in a second. But let me add a little twist to that, or an additional something. We can add marked points where the differential has a 0 of order 0. Well, it does not vanish there. It's an artificial mark point, and that will be, well, we will do that for our baby case that we do in the sequel. So if I write omega mg mu, this means that I consider Riemann surface X together with a differential form omega and a tuple of points z. Maybe I should underline it to make clear that it's a tuple of points z is equal to z1 till zn, and this sum is I equals 1 to n. And I'm requiring that these points are exactly the divisor of omega with a certain multiplicities mi prescribed, mi equals 0 included. Okay, so the first thing we did for the case of the modular surface, we said there's the Haar measure on the Lie group G that descends to the modular surface. We need the analog of that here. And that is what's called the Siegel-Veech volume form. And we have that thanks to the existence of period coordinates. So I've been drawing, well, approximately the same surface in the stratum mu equals 1, 1 from the previous page again. And I've been drawing you a bunch of closed curves. No, I shouldn't have said that. Most of them are closed, not all of them are closed. The green ones and the red ones are closed. Alpha 1, alpha 2, beta 1, and beta 2 are closed curves. They don't look that closed. Let me get back so that I get the numbers right. 3, 4, 5. For example, let me recall that this was side number 3 and glued to that side, which was also labeled 3. And now you see that beta 2 is actually a closed curve. There's one more guy, namely gamma, which is what is called a relative period. It's a path going from 1, 0 to the other 0, from the cross 0 to the black dotted 0. And altogether, these form, so the set alpha 1 through beta 2 together with gamma 2 is a basis of relative homology. Of homology of the surface relative to the zeros of the differential form, say, with integral coefficients. And if I pick such a basis of relative homology and compute the integrals of homology of omega, then I get a bunch of numbers in c to the 5. Well, you could do it in that example that is drawn to us, and the statement is that these are local coordinates. Okay, these are local coordinates, and there's a pretty canonical normalization because we take the Eisenstein, the Gaussian integers z adjoint I, in the complex plane here raised to the 5th power. By the way, this means that the dimension, the complex dimension of that stratum we're just looking at is equal to 5, and these local coordinates also prove that this is a smooth manifold, and in that way we get a measure, at least locally on those charts, which is just Lebesgue measure with a z adjoint I integer cube normalized to be 1. This gives a well-defined Lebesgue measure on omega mg, well, mu for any mu. I wrote it down 1, 1 because I'm doing that special case at least on that slide. And well, what do we really want? We want a finite volume form. Keep in mind that's the case for the modular surface as well, and all the L2 spaces we want a finite volume form. This is obviously not the case here for this omega mg11, because we can just take the surface and scale it by an arbitrary number indefinitely, and this immediately shows that the volume form cannot be finite. What can be finite is if you restrict, if you take, we can get a one volume form if you restrict to, well, the analog of the unit tangent bundle, which is all those surfaces X whose area with respect to the form omega is equal to a constant, let's say the constant 1. So this would mean just to take all the surfaces that measure on the if you cut out the piece of paper and measure its total size, then you get 1. And on this and disintegrating the Lebesgue measure on that surface with area 1 gives in fact a finite measure. I wrote here one version of the disintegration, and the Möller-Veech volume form, as I said, is the corresponding finite measure on this strata area 1 hypersurfaces. This H is not a very great notation. It's usually an abbreviation for holomorphic, because people thought about holomorphic abelian differentials. Maybe a better name would be to say this is the area 1 part in omega mg11. But since this is a very lengthy symbol, let me stick to this short symbol H, and keep in mind that this means I'm taking the area 1 hypersurface. Okay, so far so good. Now we have those strata and they have a finite measure, but why should they have anything, any behavior like those, like the modular surface that were quotients of symmetric spaces? Well, on the strata, there is at least a pretty big Lie group acting. Just as on the modular surface, there it's as big as, namely SL2 is acting. So if I take, consider this as embedded in the plane, and I take any matrix A in SL2R, and to make a reasonably easy drawing, I take something like an upper triangular matrix, and it's pretty clear what should happen. So let me, take this upper triangular matrix. What happens if I hit the left flat surface with the upper triangular matrix? Well, it gets sheared like this. This is the resulting surface. Picture is a bit rough, but the point is that, let me draw the corners, that sides that were parallel before stay parallel after, and so we get a well-defined flat surface in H2 again, and that and since SL2R acts on planar polygons, this also defines an action on SL2 of SL2R on strata. So the rough upshot is that you should think of a stratum like H of mu as the analog of the locally symmetric, the group quotient G mod gamma. And if I quotient by the rotation action of SO2R, which just takes the polygon, well, and rotates it, then I get what is called a projectivized stratum, PH of mu. That you should think of that as the locally symmetric, an analog of the locally symmetric space X. Keep in mind that this is my standing abbreviation for the modular surface. Okay, I hope that I have conveyed so far to you that strata are vaguely analog to the modular surface or its generalizations, and that it makes sense to study L2, these L2 spaces. What does it mean study? Now, how did the study start on the modular surface? On the modular surface, or more precisely on its unit tangent bundle, which is the analog of h of mu, we also have an action of SL2R. And how did the Laplacian enter the picture? Well, the natural object that acts on h of mu is the center of the universal enveloping algebra of the Lie algebra of SL2, which is called the Casimir operator, and I abbreviate that with C. This acts, well, on the unit tangent bundle of the modular surface, and just for the same reason, because SL2R as a Lie group acts there, we have the action of the Casimir on the stratum. SL2R acts transitively, of course, on the unit tangent bundle of the modular surface. Here, those strata are much bigger. They are, I mean, we computed the dimensions, and already in the example of the H11 stratum, we saw a minute ago, let me flip back briefly, that the complex dimension was 5. So SL2R is a pretty small Lie group to act on it. And as a result, the leaves of this SL2R action will not, the images of the SL2R action on the projectivized strata will just have leaves that are upper half plane. It's foliated by upper half planes. It's not equal to that. Yeah, it's just foliated. And nevertheless, by the same coordinate, there's we have the foliated Laplacian acts on this projectivized strata. You can see it in two ways. Either you see it in coordinates with the usual coordinates, it's y squared d by dx squared plus d by dy squared, if you use coordinates where x and y are the coordinates of the leaf, and there's other coordinates in the transverse direction. Or you see it formally as the image of the Casimir operator acting. So this foliated Laplacian does not see the directions transversal to the leaves of the foliation, which will mean that its properties might actually be quite different from the Casimir or the Laplacian on the modular surface. And we will see instances of that. There is something that might and will compensate a little bit for this defect. There's the fact that there's another foliation, at least on certain strata of differentials. Consider again the left picture that I'm now drawing for the third time. It's again a surface in the stratum with mu equals 1, 1. And what I'm now doing is I'm sliding 1, 0 against the other. I'm shortening the blue period. The relative period on the right picture is much shorter than on the left-hand side. But all the other periods, beta 1, beta 2, alpha 1, and alpha 2 are the same. They're unchanged. I mean, you can think of it as cutting the left surface on those lines that I have drawn in thick. These are two lines because the top line is glued to the bottom line. Keep in mind that it was number 4 and this was number 4. I'm cutting off the surface at two lines, and then I just take the two bricks and slide them with respect to the other. Actually, that sliding looks a bit like if it were a real parameter, but you can do it actually using it as a complex parameter. So the sliding is locally something in R2. Well, in more general, it's in R2 to the n-1, where n is the number of zeros of the stratum. So at least if n, which is the number of zeros of the stratum, is larger than 1, which is the case here n is equal to 2. We have 2 zeros in that stratum. Then there is another foliation by relative periods. That's why it's called the rel foliation. We move the relative periods while keeping the absolute periods constant. And that gives another foliation, another Laplace operator, which is actually locally a Euclidean Laplace operator. I'm just writing delta vert for vertical Laplacian. We'll see the reason for that in a minute. In general, there's several of them. In all the examples I will consider in that talk, there's only one of them. Okay, upshot so far. We don't have an exact analog of the differential operators, but we have 2 foliations in general and the respective Laplacians in those directions that might compensate for the different behavior. Okay, next questions. How do you produce a function at all, an integrable function on such a stratum? Well, any function supported on a little compact blob in the stratum is, of course, a function. Thank you. This was not the example I wanted to hear. This has no chances of having any good property under any of these Laplacian operators. What would be any idea of constructing something that is like an eigenfunction for the Laplace operator, or at least an approximate eigenfunction for a Laplace operator, which is what you want if you want to build or detect the continuous spectrum? Well, for that purpose, let's revisit again what we've been doing in the case of the modular surface. How do we there get approximate eigenfunctions? We get them by writing down Eisenstein series. Eisenstein series provide the continuous spectrum. They are approximate eigenfunctions for the Laplacian. And how should we transform them to strata? Well, let's have a look. Let's take the original definition that I was writing down a few slides ago and rewrite what the imaginary part of gamma tau actually is. It's the imaginary part of tau over c tau plus d, and the coset summation is, in fact, the summation over all pairs of coprime integers. And yet another way of writing that, keep in mind that the imaginary part of tau is just the y, if I write the tau as x plus iy, and that the lattice scaled to unit volume is generated by tau over square root of y and 1 over square root of y. So this means that the sum here is just the sum over all primitive lattice vectors. And if I call the lattice vector lambda, then it's the argument of psi is 1 over the norm of lambda squared. Now this is an expression that can be transformed to strata. Let's look again at the left-hand side. On the left-hand side, I wrote down a lattice, or in fact the fundamental parallelogram of a square lattice, and I wrote down for you a bunch of primitive lattice vectors. The color coding is just somehow the complexity of the lattice vectors. The blue ones are very easy ones, like 1, 1, 0, 0, 1, 1, 1. The green one is a little more difficult, and for the red one, you have to think a little bit which one it actually is. I think it has slope 2/3 or so. On the right-hand side, you see for yet once again our favorite example of a flat surface of an element in the stratum with signature 1, 1. And you'll see a bunch of things which are called saddle connections. These are straight lines between zeros. Straight for the metric given by the one form omega, and again there's several examples of them, certainly not all of them, and the color coding is again by complexity. The blue ones are pretty easy to see because you just go across this the surface. The green one is, for example, a little harder because you have to keep in mind, in order to understand that this side was glued to that side. So when you go out at that spot, you enter at the other side. So the green one is actually a saddle connection. And again, the red one is the same thing, and it's yet a little more complicated. So on any flat surface, there's a huge zoo of those saddle connections, as you can see, and you will find many more. And just as for the lattice, the number of lattice vectors of a given length r grows with r. It grows quadratically with r. And the same theorem holds, I wrote it just as a remark here, the number of saddle connections of length bounded by r in any flat surface x omega grows like r squared. It's a constant times r squared plus lower order terms. And it's actually pretty interesting to determine what the c is and how it depends, and what lower order terms here actually means. It means how to give good bounds for the next term there. But I don't want to enter that. I just want to have you remembered that this property means that whatever you are used to write down as series in the lattice case, which depends on quadratic growth of the number of lattice vectors, works just as well for the case of saddle connections. Okay, so we can make that formal to provide a bunch of functions that will have interesting properties. And these functions are called Siegel-Veech transform. Siegel used that for the case of lattices. I don't know exactly, in his book, Geometry of Numbers. The analogy by Veech stems from the 1990s. So what we do is we take a function compactly supported. You could do better, but compactly supported in R2 is the easiest thing for convergence, to ensure convergence. And then we take what is called a configuration of saddle connections. You could think of a configuration meaning just plain all saddle connections. That works. It means, technically, it means that this is an SL2R equivariant subset of saddle connections. So if you have, it means selecting the saddle connections on one surface, so that if you do it on a surface which is an element in SL2R times your original surface, you get a set which is SL2R times your original set. If that was too abstract, think just of a few examples. Namely, take not all saddle connections, but just the saddle connections connecting a zero to itself, prohibiting those that go from a zero to a different zero. So I'm flipping back. So, for example, the diagonal blue one that I'm redrawing here, this one goes from a zero to itself. This one goes from a zero to the other zero. And this one goes also from a zero to the other zero. And you can group the things. This one goes from a zero to itself. At least you now saw instances of both kinds. And as, in general strata, there's a huge variety of these things. You can, for example, think of the saddle connections connecting a simple zero of order 1 to 0 of order 7, if such a thing exists in the strata. It is not easy to say exactly what all the configurations of saddle connections are, and that's a major geometric problem, and that's very much related to L2 decompositions of strata. If you have chosen such a configuration, you can write down the Siegel-Veech transform of the function f with respect to the configuration evaluated at your given point of the flat surface. Namely, you take all the periods of these lattice vectors, you integrate them, you measure the complex length of these saddle connections, and this gives you a number in R2, or in C is always identified with R2 in that setting, and you take the function f, which eats a number in R2 and spits out a real number, and so you get f of f of lambda. So if you take the simplest case, which is the stratum h of 0, what does it mean? This means differential forms 0. This means the genus is 1. Because the entries sum up to 2g minus 2. And this means that the differential form has no zeros and a marked point. Yeah, this is exactly what you want from in a torus. The holomorphic differential form on a torus has, of course, no zeros if it's the non-zero differential form. And you add one marked point. The space of torus has always a marked origin. So this is just the modular surface. And this is somehow the baby case. This is really a case that is well studied. And we take the case of all primitive lattice vectors as our configuration. And we take the function f, which is, up to rescaling just the function f is psi of 1 over norm of lambda squared for psi, a compactly supported function on the reals, positive reals, as always. And then the Siegel-Veech transform with respect to that configuration and with respect to that function f is just the truncated Eisenstein series, the psi truncated Eisenstein series, as we have seen it on, let me flip back a second. On this slide, you just put the two formulas on top of each other and you find that. Okay, conclusion. The Eisenstein series that usually produce the continuous spectrum, they should be thought in general as Siegel-Veech transforms on strata. Let me go really now to the baby case that I want to study and that I can really decompose. The case H00. What does that case mean? What does H00 mean? It means that we take an elliptic curve together with a holomorphic differential form. Two points which are zeros of order 0 of the differential. They're just two marked points. Because it's an elliptic curve, we can always move one of those points at the origin. That's why I write it as 0. And the other point is a point z, and I will usually use the coordinates u plus iv for that point. This point is not 0. And keep in mind that h meant the global area normalization, which is the area, which is a rescale. If I take the projectivized stratum, then I also rotate the differential. But if I also rotate the differential and I know that the area is 1, then the differential form carries no information anymore at all. So the projectivized stratum H00 is just the elliptic curve with two marked points. And I think this is actually a stratum or a space that is very familiar to many number theorists, and there's many papers that have the title Jacobi somethings that have been written on that stratum, except I don't think it has been analyzed from the point of view that we will in the sequel. One more reduction step. There's, of course, projections. I can forget the first point or can forget the second point. In any case, forget one of the 2 points. This gives me a projection map pi onto the unitangent space of the modular surface. And this means that there is a big chunk of the L2 space, which is sort of well known. Namely, I can integrate along the fibers to get a map from the L2 space of my H00 stratum to the L2 space of the modular surface. And by pulling back functions means so that they are now constant along the fibers, I get a map in the converse direction. And so this means that inside the L2 space of H00, I have a copy of the L2 space of the modular surface. And what is and since that is very well studied, what is left, I declare it to be the genuine part, and I call it just L2 gen, is the orthogonal complement of that space. So that's the space I'll be really interested in. So what about configurations for A00? I was, well, pretending that with Siegel-Veech transforms, we should get the continuous spectrum, sort of, the analog of Eisenstein series. And so what are the configurations here? Well, you can join, take saddle connections joining a zero to itself, because these are closed, these give absolute periods, and we call them C-abs. Or you could do the opposite thing. You can take the saddle connections that join 1, 0 to the other one. So if this is a point in space, and this is the 1, 0, and this is the second 0, I'm drawing the same picture twice. Then in the first case, I would take the absolute periods. This is an example, and this is an example. And in the second case, I would take this as an example, or, well, more complicated friends of it. I hope it is clear what I mean by the set of all absolute periods and all relative periods. Well, the absolute periods, they don't depend on the location of the second 0 at all. And so it's pretty clear that they produce a subspace of L2 of the modular surface, the copy that sits in there. And in fact, what they produce pretty much, but what we have already seen about Eisenstein series and their rewriting in terms of Siegel-Veech transforms, that this is just the Eisenstein space of the modular surface. And the Siegel-Veech transforms of relative periods, they of course depend on the location of the second point, as can be seen from the green picture. So they should and they will produce something that belongs to the genuine part. And actually that's not totally trivial, but it follows from all the rest, because the genuine part was defined as the orthogonal complement of the other space. So to see that this is L2 orthogonal to the rest requires a computation that follows from what happens in the sequel. So let me ask somehow in this baby case the guiding questions we can answer in that case, and I would like to answer in the case of general strata, namely whether we have listed all possible configurations in that way. It seems so, but the answer will turn out to be no. Whether there is a notion of cusp forms which agrees with a perp of all Siegel-Veech transforms, and where ideally on the space of cusp forms our Laplacian has just discrete spectral. Well, actually, our Laplacian, it's not clear what our Laplacian should mean. There's the foliated Laplacian, and maybe the better behaved guy is a guy that involves both foliations. The foliation by SL2R orbits, which is the lambda fol, and also the other foliation by relative periods, which is now really along the pi fibers. So this is here, in that case, along the pi fibers. Pi was the projection to the modular surface. And maybe that what we call compound Laplacian behaves better. And I can foresee, yes, it will at the very end of the talk. Before I answer these questions, let me summarize the known results. There's basically one result for general strata. There's quite some results for Teichmuller curves also should mention that Claire with Amos Neveu, René Rühr, and Barak Weiss have something in that direction and interpret at least the case of one-dimensional strata. But for higher dimensional strata, there's basically one result, although it's a really major result, by Avila and Güzel, dating 10, 15, almost 15 years back, and which is, well, sort of a weak version of the Selberg conjecture for strata, namely that for any stratum, and for those who know, even more generally for so-called linear submanifolds, the following property holds. Whenever I'll move a little bit away of a quarter, I fix myself a delta, which is positive, and I consider the spectrum of the foliated Laplacian in the interval 0 and a quarter minus delta. There's only finitely many eigenvalues with finite multiplicity. The true Selberg conjecture has been, what about the spectrum intersected with 0 or 3 over 16? That has been raised for strata as a question of Yokos, and at least also dating 10 years, if not more, back. I don't think there has been any progress in that direction. To give a one-sentence idea of proof of that theorem, let me mention that they don't study the Laplacian or the Casimir, but they rather study another element in the Lie group, or sort of the flow, the diagonal flow in SL2R, e to the t, e to the minus t, and the corresponding differential operator. This operator sort of behaves very, very well because it contracts in some directions, behaves very badly in other directions because it expands. And so the trick that they use is to work on a fancy Banach space instead of the original L2 space, where this operator can be shown to be a quasi-compact operator and not compact, and so they really lose control around the quarter. And this doesn't give you directly something on the L2 spaces, but since there is a good classification of SL2R representation and we know all about their eigenvalues, knowing something about that operator is just as good as knowing something of the L2 operator. If this was way too quick for you, it's maybe also way too quick for me, but I said those 3 sentences about their proof just to mention that the words boundary, cusp forms, and Siegel-Veech transforms do not occur anywhere in their paper except for a sentence where they explicitly say that they don't study these spaces. Because the boundary of strata is complicated, because they don't want to control cusp forms, and with their approach, at least for that theorem, they don't need to. So the analog of Eisenstein series is a totally uncharted territory for strata. In the last couple of minutes, let me try to state the results we have. So the baby case of H00 is really an exception. These strata usually are not homogeneous spaces. These strata have an action by the Lie group of SL2R, but of no bigger Lie group. And if I neglect measure 0, the space where the 2 points collide, this stratum H00 is a homogeneous space just for the special affine group, and I abbreviate that by G prime. And in general, if you see a prime, that usually means the Jacobi version of the unprimed thing. So it's usually the obvious semi-direct product of something. So up to measure 0, coming from the collision locus of the 2 points, the H00 is just that quotient. So if I want to study the corresponding L2 space, I can describe not only the decomposition into the L2 representations, but I can first describe the decomposition into the G prime representations, into the representations of the bigger Lie group. makes me, well, in that case, I should mention another player which helps me classifying that. Namely, C, recall, that was the Casimir of SL2R, which was acting on every stratum and on the modular surface. And although the group G prime is not a reductive group, there's a nice, the center of the universal enveloping algebra is very nice here as well. It's a polynomial ring generated by some element C prime, which happens to be a degree 3 element. And that gives another, well, in quote, Laplace operator, which we call the total Laplace operator. It's a degree 3 operator, and it will help us classifying things and sorting things out. Okay, I can now finally start stating the results. Namely, first, the unitary irreducible representations for the big group. They are very well known. This is a group, is a semidirect product, and irreps for semidirect products have been classified by McKay 50 years ago. And here the answer is they either factor through the group SL2R, G, or they're induced from the group N prime, which is sort of the upper triangular thing. It's isomorphic to a Heisenberg group. It includes the translational part and the upper one off-diagonal entry. So the actual representation, chi and m, is written down in coordinates explicitly. It comes from a character of an R2 inside that Heisenberg group with parameters n and m. And two of these representations, n1 and m, with indices n1, m1, respectively n2, m2, are isomorphic if the expression n1, m1 squared, this expression agrees for the two groups. And that means also that this Casimir C prime really detects isomorphism classes of these representations, because the eigenvalue on that representation is, well, the prefactor is an artifact of normalization, but here you really see the representation. Okay, so this means we know in the genuine part, keep in mind those that factor through G will not appear in the genuine part that I said I really want to analyze. In the genuine part, we know all the representations that should appear. And now the first of the theorems in the paper I'm reporting about is that the genuine part decomposes into those representations pi and m with just that index set listed n in z and m from 1 to infinity. Keep in mind that this isomorphism class is just given by nm squared. So the number of times a representation occurs, a given representation, is the number of ways you can factor any number as n times m squared. It's natural to keep this nm as is, because it gives you a hint of how you realize these representations. And in the interest of time, I will not go over the precise formula and comment on questions. You can really write them down. You can really write down a certain Poincaré series and check that these representations that you write down for any beta with suitable growth conditions give functions that transform as prescribed for functions in that induced representation. And the converse.
Sorry, Martin,
Yes.
Parameters tau and z here, what's the
Yes.
then x, y, r, what corresponds to what?
Yeah. Good. Oops, good point. Let me find the page again. Tau is x plus iy, and z, this is in the upper half plane, and z is the complex variable is u plus iv. Yeah, thanks. If you're confused why there is a v over y floating around, this is maybe an artifact of what you might call choosing bad coordinates. Sometimes it's convenient to represent z as u plus iv, and sometimes it's convenient to represent it as multiples of tau plus a real number. And if you do that, then there's no fraction appearing there, but then you have bad expressions at other places. So in one direction, this is you realize these representations by Poincare series, and conversely, you get the converse map by integrating out against the certain representations chi and m. And if you check that converse map, you see that the coefficient is non-zero if and only if the following properties holds of the for the function f. And this highlights our main technical player, namely a certain Fourier-Heisenberg decomposition. Yes, Fourier decomposition should be made for abelian groups. No, a Heisenberg group is not an abelian group. So the Fourier-Heisenberg is a kind of strange terminology. And what I really mean here is that you decompose first with respect to an R2 in the Heisenberg and refine a certain coefficient where you're sort of constant in the U variable, R equal to 0. You refine it further with respect to the third variable in that Heisenberg group. Since my time is up, let me not go into that, but let me state very briefly the remaining theorems. Once we have classified the decomposition into G prime representations, we can restrict all those representations pi mn from G prime representations to G representations and see how they decompose into the standard discrete series D and principal series I. There's no complementary series appearing here. So this is a statement we re-derived. It could have been done by Mackey. Maybe he did it. We didn't locate it. But this tells us all representations that occur in the genuine part of L2. So with theorem 1 and 2 combined give the complete answer for the representation theory. And theorem 3, let me just state that, is that the Siegel-Veech transforms, they are actually in the kernel of that funny additional Casimir operator C prime, and they are contained in the representations where the first index is 0. And in fact, they make up for all of these representations. So let me say that the Siegel-Veech transforms in that way are not responsible for all the continuous spectrum of the foliated Laplacian. Keep in mind that in the first row, we see that there's continuous part both in the pi n m restrictions and in the pi 0 m restrictions. And the Siegel-Veech transforms only contribute to the pi 0 m restrictions. So that's an artifact that the foliated Laplacian is a bit bad. And without going into further details, let me say that the compound Laplacian that I introduced, which is the foliated Laplacian plus a little bit an epsilon of the vertical Laplacian, that cures that defect. And if we do that, then things become right again, and we get the expected behavior as in the case of the modular surface. Okay, thank you for your attention.
Thanks a lot. I'll first stop the recording and then take questions.